Hello, and thank you for joining me for another topic in chemistry. Our focus today, now that we have a pretty good understanding of how matter is grouped together, as chemists, we want to talk about how do we describe matter? So that's matter's properties, and how does it change? That is the focus of chemistry, is being able to describe things, explain things, and when stuff changes, that's when interesting chemistry happens. So go ahead and set up your note page for today with our topic. Our essential question today, we actually have two. One of them is, what is the difference between physical chemical properties and physical chemical changes? And then I also want you to be able to answer the question, what are the 5 signs of a chemical change? So put these essential questions at the top of your notes. The idea here is that those are the questions you should be able to answer in your summary when we're done with our notes today. If you cannot answer those questions, you need to go back and look at your notes a little bit. You need to ask me for help. You got to do something to clarify the information. So that is our focus for today. Let's get into it. So let's start with the term physical property. A property is some type of adjective in chemistry. It describes an object. Because it's a physical property, it means you can determine the property without changing the identity. Think of your senses. What does it smell like? What does it look like? What does it feel like? Texture, color, size, the weight of it, or how dense it is, those kinds of things. So, for example, imagine this pizza was sitting in front of you. What properties would we say? Well, you might say that it smells spicy or cheesy. You might hear it sizzling if it just came out of the oven. If you feel it, it might be hot. It might be kind of like like slimy a little bit because the cheese and the grease. It looks round. It's orange and red. It tastes salty, spicy, those kinds of things. So those are all things we can use to describe an object. There's definitely a place for physical properties. Anytime you're doing a lab and you're trying to describe what you see, those are physical properties if you're just describing it. Now, you can use a measurement tool, like what is its mass or what is the size of it, those things. So you might use tools, but you're still just getting the information by observing. That's what makes it a physical property. A chemical property then is still a description, it's still an adjective, but now you're describing, will it take part in a chemical reaction? Now, without prior knowledge, you're not going to be able to just look at something and see, oh yeah, that will take place, or that will participate in chemical reactions. You have to do some sort of test to see if it has that property. So, for example, if something is combustible or not, you have to light it on fire. Now, you have prior knowledge with lots of things in your world to say, oh, this piece of paper will light on fire, this rock will not light on fire. But at some point, it was because somebody did a test, or you saw it, or you tried it, and then you knew it had that chemical property. So you can't just look at something and figure out if it's combustible or not unless you have previous information. You would have to test it. Same with rusting. Now, again, you have an idea that certain metals will rust and like plastic will not produce rust. But again, that's only because of prior knowledge. If you want to know if something will rust, you have to let it have the opportunity to rust. Same with mold. Will it or will it not mold? That's an example of a chemical property. Or will it react with acid? If you want to know if it reacts with acid, what do you have to do? That's right. You have to put it in acid. So even if the answer is that it does not react with acid, that description is still a chemical property. So just to clarify, so whether it does or does not do the thing you're testing, that doesn't change the fact that either way, you're testing that chemical property. So physical chemical properties. Property is any type of describing idea, and whether or not you have to change the identity or test it is what makes it chemical. If you can tell just by looking at it or observing, then that's a physical property. So properties are useful for describing something that's going to happen, especially in a lab or an experiment. Okay, so that's the first chunk of our notes. And so I'm going to have you take a little break. The reason I do these brain breaks are 2 reasons. One is because it gives you kind of an idea of how many notes we're going to take today. We're already the first chunk of our notes done. And there's only 3 chunks because they go with the 3 levels of Costa questions. The other reason I want you to take this little break is I want you to think about the information you just heard. Does it make sense? Can you fit it in your brain? Can you process it? There is a guide on Schoology in the week 2 folder to help you write high-level Costa questions. But if you need a reminder. So right now you're writing a level 1 question. You could put it in the side margin of your page so that you can find those questions for reviewing later. Remember, I'm trying to give you strategies of learning from your notes instead of just writing down words because you're supposed to take notes. Like, what do we do with these notes? We write questions, we review them later, that kind of stuff. A level 1 type of question comes right from the notes. So here's a list of some different keywords. Like, you could do a definition, you could do a description, you could complete a sentence. But there's some other really good Costa questions sentence starters on that guide on Schoology. You could either download this in Notability. If you have access to a printer, you could print it off and put it right in your notebook. That would be a good resource. So take a little break right now, pause the video, write your level 1 question in your notes. All right, welcome back. Now let's talk about changes. So just like there's a physical and chemical property, there are physical and chemical changes. A physical change then is something that changes the properties. So something happens, but it doesn't change the identity. So think of it this way. If you were to list the ingredients before the change and after the change, the ingredients would be the same, even if it looks physically different. So it looks different, but the same chemical makeup. That's kind of the idea. So for example, if you break your arm, now you might even notice that your arm has kind of a new shape or something's different about it or it feels different, but it is still your arm. The bones are still present, the skin, tendons, all of that is still there. It's just it looks different. If you paint a fence, the paint particles used to be in a can maybe, and the particles of the fence used to be able to be seen. Now you've just covered up the fence particles with paint particles. You've just transferred particles, so it looks different, but the chemical makeup is still paint, it's still wood, it's still a fence. It just looks different. If you let something melt, you haven't changed the ingredients. So even though we call it ice when it's frozen and we call it water when it's not frozen, they are the same chemical identity, the same ingredients. It just looks different. And same goes with dissolving. So if you take frozen concentrate like orange juice like this and you mix it with water, it's still the same particles. They're now just mixed with water and they're more liquidy instead of frozen. So the same identity, the same ingredients, the same chemical makeup, they just look different. So that is a physical change. So you think about before and after, have the ingredients changed? If the ingredients haven't changed, but it looks different, that's a physical change. A chemical change is where you have changed the physical properties. It looks different, but you've also changed the chemical properties because the identity has changed. It's a new identity with new physical and chemical properties. It looks different because it is actually different. So a great example of this is the Statue of Liberty. It is possible you've seen this picture before. When the Statue of Liberty was first built, copper is something that's considered very regal, very expensive, very fancy. So they built the statue out of copper just to show how important it was. Well, after time, this green stuff started to form on the outside of the copper. And so for a little while, they would scrape it off. But then suddenly they noticed that the areas where they were scraping it off were getting thinner because the copper was reacting with oxygen in the air and creating a new identity on top of the copper that was there. So when they scraped it off, they were scraping off copper, the new particles, leaving less behind. So eventually they were like, you know what? We have to let the whole thing change this greenish color. Otherwise, we're going to have no statue left if we keep cleaning it off. So that's an example of a chemical change. It looks different than when it started because that green stuff is an actual new identity. So a chemical change. Chemical change is something where you think about the ingredients before and after. Would you call it something different afterwards because it's a new actual identity, or does it just look different? This one can be kind of tricky though, because you might be thinking, well, wait a second. Like we said before, like when it's solid, we call it ice, and when it's liquid, we call it water. We call it something different, but the identity hasn't changed. So how will we know if the identity is actually changed? That's a tricky one. That's what we're going to talk about next. For now, though, here's your second brain break. So again, giving you kind of an idea of how many notes are left, we're already 2/3 done. So go ahead and pause the video. A level 2 kind of question, you can use it for review for future reference. A level 2 means that there's a hint in the notes, but your brain has to finish the answer. So these are things like compare and contrast, explain something, sketch. Those of you that like to draw, sketch is a really awesome level 2 question. Like give some sort of picture representation of a physical change. Like that would be a really cool use of your skills and something that's, kind of fun to do. So that's a level 2 question. Go ahead and pause. Remember, there is that Costa Questions guide on Schoology to help you write sentence starters if you want to. So much for joining me for more chemistry demo time. All right, so the idea is that you already have understanding of the difference between a chemical change and a physical change. But if you think about those definitions, physical change looks different but keeps the identity. Chemical change looks different because it's a new identity. It's kind of tricky thinking about, well, how do we actually know it's a new identity? How do we know that there's new bonds forming, that there's actually a new chemical composition? That's kind of difficult to tell because sometimes it might not look a lot different. So the great news is that chemistry gives us some signs. So what I'm going to show you is what are the 5 signs that if you are observing some type of change, you know that if you see one or more of these things, you will know that it's a chemical change, not just a physical change. All right. So the first thing I'm going to show you is I have 2 chemicals here. This one happens to be called ammonium nitrate. It looks kind of like white beads, or kind of like, when styrofoam falls apart, like those little white beads. That's called ammonium nitrate. And then I've just put it in a baggie. And then the other one I have is calcium chloride, which kind of looks like white chalky sort of pieces, like crunched up kind of like hard pieces like that. So calcium chloride. And then what I'm going to do is I'm going to add some water to them. So right now, I'm going to give you a hint about what we're going to notice. Right now, we have, I'm using a digital thermometer. So you can see that, it looks like it's about 23.1, about room temperature. And what I'm going to do is I'm going to put some water in each of these baggies. And then we're going to see if we notice anything change. Okay, so you can see that one. I got some water in it. Looks a little bit cloudy. And then let me do the same thing. Some water in it. This is called deionized water, meaning that the only pieces floating around in it are water pieces, no other hard water, soft water kinds of stuff, like no other minerals. Okay, so remember that original temperature, all right? And then what I'm going to do is I'm going to put them in here. So you see what they look like now, just basically what you would expect. So right now you might think this looks like a physical change. But what I want to show you is I'm going to go ahead and put the thermometer in here. And let's see what we notice. Can you see it? There we go. All right, so look at that. So definitely an increased temperature, 42.1, 42.2, 43 a little bit. So definitely we see, there we go. Let me get a little bit more in there. So remember, it started at 23, and look at that change of temperature. Not something you would have noticed just by looking. If you were here, you could feel it. It definitely feels warm. So a temperature change that happens on its own is a sign of a chemical change. All right, well, I've got this other baggie. Let's check out this. I did just clean this off in between, so let this get back. All right, it's cooling down, it's cooling down. I'm not gonna wait for it. I'm just gonna put it in here and see what we notice now. Look at that. So we are down to 4 degrees, 3 something. It just keeps getting lower and lower and lower. So remember, it started at 23, and then we got it up to, high 40s with that other baggie. And now you can see we're down to less than 1 degree Celsius we're using to measure in chemistry. So we end up with this really cold temperature change, even to the point of negative. Now, it's not frozen because it's not just water. Water freezes at 0 degrees Celsius, but it's even colder than that, showing you that these particles are doing something to change the amount of energy within their structure. And again, you would feel that this is pretty cool, like quite cold actually, based on that room temperature. So we see a temperature change. We observed it using a thermometer, and then also we can feel the container. Notice I didn't stick my hands inside the container, but if this was in a beaker, in a lab, you would be able to take the temperature or observe it by feeling the container. So when chemicals are mixed, so there's some type of reaction that you have started, and those particles change temperature on their own, that is a sign that you are creating some type of new identity. So a temperature change, either hotter or colder, when you didn't add it, you didn't heat it up, you didn't put it on a Bunsen burner, in a microwave, or a hot plate, but it happens on its own, that's a sign of a chemical change. All right, let's do the next one. Let me just kind of set some of these things aside here. Okay. This next one I'm going to do, so what I have here is I have a piece of cotton. Basically, it's kind of the cotton you would use like if you were gonna make a stuffed animal, or you get it from a craft store, so just regular cotton there. And then what I have is something called sodium peroxide. Sodium peroxide, if you kind of see here, it looks kind of like little yellow beads a little bit. And I'm just gonna make a little bed of some of that sodium peroxide and the cotton, and that's it. Okay, technically there's a little bit more. I'm also gonna put a few drops of that same water I used in the last demo. Now, if you were close by, you might hear some sizzling happening. That's interesting. So there's like some sizzing and some fizzing happening, but then let's see if we notice anything else going on. Can you hear that sizzling? All right, definitely there's something happening here. So the fact that we were able to produce fire by adding little drops of water tells you for sure this is a chemical change. Let's think about all the things that happen. For sure, a temperature change, like we just learned, if the temperature change happens on its own, we know that's going to be a chemical change. Fire implies that there would be a temperature change. But the other really cool thing you saw was light. So light being produced on its own from the chemical reaction is a sign that it's a chemical change. So this new stuff that I have here, it doesn't look like the stuff that I started with. So that is a sign that this is a chemical change, not just a physical change. Yeah, it looks different, but it looks different because it's a new identity. How do we know it's a new identity? Temperature change, light given off. And then there was that fizzing. We'll come back to that in a little bit. So definitely a sign that something new has been created. So we've got two signs of a reaction now. So if you're doing an experiment and you see a temperature change or you see light given off, this is a sign that this is a chemical change. All right, the next one I want to do involves a couple different liquid chemicals or solutions actually. This solution happens to be called potassium iodide. You can see that it really just kind of looks like water. It happens to be potassium iodide mixed with water. That's what makes it a homogeneous mixture, a solution. And then my other chemical I'm going to use is lead nitrate. Once again, kind of looks like water. So I'm using two chemicals that are called aqueous solutions, meaning the chemical is mixed with water to create a solution. And you can see they both kind of look similar. Now, if I were to ask a kindergartner, if I take something that looks like water and mix it with something with water, they might be like, oh, nothing interesting is going to happen. Or because they're in kindergarten, they might make up some wild story. Well, it turns out they might be right. Okay, so I pour in one of my solutions, and I take a look at my other solution, mix them together, ta-da! Chemistry happens, yay! Okay, so let's think about what happened. For sure, there is a color change. That's the thing that you notice right away. But I also want you to notice, as I bring it a little bit closer, do you notice that there's kind of like some chalky collection at the bottom? That is a precipitate. The definition of a precipitate is a solid that forms from a chemical change between two solutions. So it's not any time you produce a solid, right? So if you boil off water and there's like a crusty solid left behind because there was something mixed in the water, that's not a precipitate. A precipitate is the result of a chemical change between two solutions. We know it's a chemical change because if you looked at the way that those two solutions looked when they started, they looked clear, right? They looked like water. You couldn't see any particles in them. Now you can see these particles that have settled to the bottom. That is the precipitate. So this demo actually produced two signs of a reaction. A definite color change that was unexpected. So for example, a color change that's not expected is if I take a black marker and I color on a white piece of paper, it turns black, or any other color, or paint, or food dye, or any of that. Those are expected color changes. You haven't changed the identity, you have just changed the look of it. So that's physical change. But a color change, especially in addition with my precipitate, definitely an identity change. The starting chemicals looked different. The ending chemicals look different because it's a new identity. So we've got temperature change, light given off, color change that's unexpected with something else, and then this happened to be precipitate. All right, so we've got 4 of our 5 signs of a reaction. Let's go back, or let's finish it up with our last one. So what I have here is just a big metal tray, but then inside it, I've got It's hydrogen peroxide. Now remember that other demo with the cotton used sodium peroxide, looks very different. Hydrogen peroxide you might even have at your home. Maybe you've used it for cleaning out cuts because the chemicals of hydrogen peroxide can kill cells. Now the tricky thing, the reason it hurts when you put it on your skin is that hydrogen peroxide doesn't know the difference between bacteria, germ cells, and regular healthy cells. So that's why you don't just use it to like wash your hands because it would kill any cells it comes into contact with. You would just want to put it on, a cut or a scrape or something to kill any bacteria. So that's what this chemical is, hydrogen peroxide. So I'm going to put some hydrogen peroxide in the bottom of this graduated cylinder. And you can see that, okay, sure, there's some little fizzy bubbles that form just because I poured it kind of fast. But other than that, I don't really see anything happening. So the tricky thing here is that this is a reaction that is actually happening. Hydrogen and oxygen are pulling apart from each other from the hydrogen peroxide. Now, you might be like, well, yeah, right, Ms. K, I don't see anything happening, right? So there's no signs of a reaction to prove that something is happening. Well, you might know, well, wait, hydrogen and oxygen, they're both gases. So maybe the reason we don't see it is because they're just floating away and we can't tell. So why don't I add some soap? If I add some soap, maybe that will trap some of those gases, and then maybe bubbles will appear, and then those bubbles will be the sign of my reaction. Okay, so let me mix that together. Okay, so definitely you see a little bit of bubbles, but now as I let it sit there, does it look like it's changing at all? Not really anymore, right? So either this is a dud of a demo, which I hope you trust that I'm not going to choose a dud of a demo for you, or there's something else going on. So the tricky thing about this demo is that it happens really slowly, and sometimes that's the case. Reactions take longer to happen depending on what is going on in that reaction. So I'm going to use something called a catalyst. Now, maybe you remember from biology that an enzyme is a catalyst that happens in a living cell to speed up reactions. Sometimes it's, we use it to get nutrients from foods. A catalyst is just something that speeds up a reaction. So I told you this reaction is happening, but it's happening really slow. Let's speed it up and see if we can get our fifth sign of a reaction. Let's see what it is. So I pour in my catalyst, and then what do we notice? Ta-da! Okay, so definitely something is happening now. Check that out. So now for sure there's bubbles, and then look at this. This tells us what? Temperature change, you're right. But the bubbles tell us that what is happening? Gas is given off. If you were here, you could smell it also. Now think back to that demo with the cotton. I told you that we could hear fizzing. That was also a sign that gas was being given off. So fizzing, bubbles, smell. If you can smell something that wasn't there before, that's a sign that a new identity has been given or produced, and it has a certain scent. So this one, you can see temperature change. You can see gas given off. And then there's also a little bit of a color change. You might be able to see kind of this yellowish color. So definitely signs of a reaction. So the stuff that's here is not the same identity as we started with. It looks like it would be fun to touch. The tricky thing though is that hydrogen peroxide might not all be used up. So these bubbles could actually be really painful the way that hydrogen peroxide is. So even though it looks really fun and like you want to touch it, it's not safe to touch it. Okay, so let's review really quickly. What were the 5 signs of a reaction? So if you're doing a lab and you're observing what's going on, these are the things you're looking for to see if there was a chemical change or chemical reaction. Did the temperature change on its own? So then you have to make sure you measure and observe before and after. Did the color change on its own? Is there a precipitate produced? Is there light given off? Is there gas given off? Those are the things we look for to decide whether or not something is a chemical change. Thanks for joining me for chemistry demo time. Bye. All right, so just to make sure that you got all of those signs of chemical reactions written down, maybe you were just so in awe of the demos you forgot to take notes. So there's 5 signs of a chemical reaction. One of them is a temperature change on its own. So if the particles have heated themselves up or cooled themselves down as they're changing identity, this is a chemical reaction. Now, this doesn't mean that you have heated it up in the microwave or you added heat to it, but if the particles change temperature on their own, this is a sign that a new identity has happened. When light is produced, this is a sign that a new identity, the original chemicals did not give off light, the new chemical does. Color change. Well, color change, remember, can be tricky because you can come up with a physical change that is a color change. So, color change, we say, is not enough by itself because sometimes the identity doesn't change, it just looks different. So, usually we're going to say a color change needs to happen with something else for now. The more chemistry you learn, the more you'll see that color change could be a sign of a chemical reaction. You just have to know more about what's going on. A precipitate is formed. So remember, a precipitate is a solid that forms when two solutions are mixed. It's a very specific definition. It's not just seeing a solid present. So if there was a solid at the beginning and there's a different solid at the end, that's not a precipitate. Or if you boil off water, that's not a precipitate left behind if something was left behind. A precipitate has to start with two solutions. Remember, that's a homogeneous mixture of some kind of chemicals that can react with each other, chemical reaction, chemical change, to create a new compound that is a solid. So when that happens, for sure, we're like, oh, yeah, something new has been created. And then if a gas is given off. And again, don't let a change of matter from liquid to gas, for example, boiling water. It looks like there's gas given off, but that's just the water particles turning into water vapor. That isn't the same thing. It has to be a new identity of a gas. These are the things we look at to decide, okay, there's a new identity. It doesn't just look different, it is an actual new thing. So this is how we know it's a chemical change instead of a physical change. All right, so the next thing I want you to do real quick, kind of to make sure you remember these 5 signs of a reaction because they're so important in the lab. I don't want you to have to just like look them up. I want you to know them. So on an output page, I'd like you to trace your hand with 5 fingers. Out of the tip of each finger, draw a picture that helps you remember the 5 signs of a chemical reaction. So draw a picture that represents gas given off, light change or light given off, color change, temperature change, precipitate. So just some like picture or symbol to help you remember it. And if you add color, it will make it easier for your brain to remember it. That's like a brain trick if you didn't know about it. That's why highlighters were invented. If you highlight things, your brain remembers it because it sticks out in your brain because of that color compared to everything else. So if you add a little bit of color to your pictures, that's going to help you. So this is a quick little processing assignment to help you remember the 5 signs of a chemical reaction. And that brings us to the end of today's topic. So go ahead and do a level 3 question. Level 3s are kind of fun, open-ended, creative, brainy kinds of questions that generally don't have right or wrong answers as long as you have logic in your answer. So it could be things like argue for getting rid of physical properties in labs, or judge which type of what is better, a chemical change or a physical change. You know, those design a lab that shows a physical change, those kinds of things. So go ahead and pause the video and write your level 3 questions that you can use as a review for the future. All right, that brings us to the end of our topic for today. So if you did not already do so, go back and finish your CASA questions, write your summary for today, and remember the summary should answer your essential question. There is an assignment called Matter, so it's a matter processing assignment on Schoology. Work on that. It reviews classifying matter kinds of things and chemical physical properties and changes. There are unit practice problems, remember. They are currently in the week 2 folder. They go in the back of your notebook. You just start on the last page and work backwards. You only have to put your answer. And remember, if there's multiple letters, like if number 5 has A, B, C, D, E, F, you only have to pick one of them unless you feel like you want more practice. Those unit practice problems are because it's a way for you to process, did this information make sense? I know I do have an assignment today, so that's obviously a more formal way to see if this makes sense. The unit practice problems just give you a little bit more chance to practice, obviously. That's why they're called practice problems. And remember, the answers are posted so you can check your work and let me know if you have any questions. All right. Thank you so much for listening. We will see you at our next Zoom session. Goodbye.